These are the notes on energy, which will take us to our new textbook, and the very first section, we are going to do Investigation 1, Experience 1 that goes along with these notes. We already discussed that chemistry is the study of matter, so that is its main focus. We also described what matter is, anything that has mass and volume. So you have to have mass and you have to have volume to be matter. Of course, if you have mass and volume, well, then we also saw that you have density. But it turns out you cannot study matter unless you study something that is not matter, unless you study energy. Now, energy itself makes up pretty much most things you would think of that are not matter. Now, energy is a little tricky because it can be contained in matter, in the position of matter or in the movement of matter, but the energy itself is not matter. So what is energy? Energy, which is a very hard thing to define, by the way, this is a pretty good definition. Energy is a measurable quantity which is capable of doing work. So what does measurable quantity mean? Well, it means it's something we can put a number on. We can get a good measurement of it. And what does doing work mean? That means basically pushing something physical over a distance. If you can push something over a distance, you don't have to have a 9-to-5 job. That's considered work in science. So it's a very, very low bar for work. For example, in the case of this classic old-fashioned mill wheel, you have water coming in at a higher elevation, dropping down to a lower elevation. Well, that's changing how much energy it contains. To change that energy, we are able to use that flow of energy to turn the mill wheel. This was a very early way for people to take the energy of water and find another use for it. And this was before we had the big industrial revolution where we could do such things with machines. This was an early way of using the energy that was around us. So the water is moving, matter is actually flowing, but energy is flowing too in this image. Energy can be divided into different categories. Potential energy is energy that is stored in a system. So think of if you stretch out a spring or a rubber band, then it's got that potential energy because if you let go, it snaps back. You can think of potential energy also as being the position something is in. If something is up high on a shelf, well, it has the potential of falling down to the floor. Those are examples of potential energy. In chemistry, a lot of times we think about potential energy as the energy in a chemical bond between two atoms. There's energy stored there that can be used in other ways. Then there's kinetic energy, which is the energy of a moving object. When any mass is moving, it has kinetic energy. The bigger the mass is, the more energy. The faster it's moving, the more energy. That's kinetic energy. It's the energy of moving objects. And that can also do some work. It can make things move. This is the little diagram on page 7 in the textbook, which does a pretty good job illustrating the difference between potential energy and kinetic energy. The stretched out rubber band has potential energy, and if you release it, then it's transformed into kinetic energy. The rubber band is moving, and some of that is also transferred into heat, which is the movement of the air molecules. You might not even see them, but some of the air molecules are now moving faster, so there's a difference in kinetic energy there as well. So energy is the capacity to do work or to produce heat. So what's the work that's been done here? Well, the movement of the rubber band. And what's the heat? Well, maybe you feel some on your hand, change of temperature of the molecules on your hand, and of the movement of the ones in the air around the rubber band. When we talk about energy in science, generally we use the joule. That is the SI unit, or the metric unit, with a capital J, and that's the one we use the majority of the time in most of our calculations. But when we're talking about heat, well, a lot of times we will use a different unit that is not the official metric unit, called a calorie. A calorie, on the right, has a very simple definition. It's the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Well, 1 gram of water is also 1 milliliter of water. So just raising a little bit of water by 1 degree Celsius, that's a calorie. But when you hear about calories, like on a label, on a sports drink, or on the food you're eating, they're not using the same calorie I'm talking about there. They're not using the lowercase c calorie, which is what I was talking about. They're using the capital C calorie, which is also called a kilocalorie. It's 1,000 calories. Notice on the bottom, 1,000 calories is a kilocalorie, or a capital C calorie. That's the kind that we measure in our daily lives. So what would that do in terms of heat? Well, 1,000 calories would raise 1,000 grams of water 1 degree Celsius. So it would raise a kilogram of water. So think about, it's the amount of energy to raise a kilogram of water 1 degree Celsius. Or it's the amount needed to raise 1 liter of water 1 degree Celsius, because a kilogram of water, liquid water, is a liter of water. Okay? So basically, a calorie is a little more than 4 joules, 4.184 joules. And sometimes we'll use one and sometimes the other, depending on the context. Thermodynamics, or thermo-D, is the study of how energy flows in a system. So when you're keeping track of where the energy is initially and where it winds up at the end, how it changes, that's thermodynamics, the study of how energy flows in a system. Your energy might start off as potential energy, it might turn into kinetic energy, or it might be transformed the other way from kinetic to potential, or it might go from one form of potential into another form of potential, or it might be turned into radiation. There's a lot of possibilities for your energy to do in a particular circumstance at any point in time, and thermodynamics sort of tracks that, keeps track of it. So thermodynamics is the study of energy flowing through a system and its transformations, but this is chemistry class. We're going to be primarily concerned with the part of thermodynamics that deals with chemical reactions. This is called thermochemistry. Thermochemistry is the study of energy changes that happen during chemical reactions or in changes of state, like from a liquid to a gas. When you're talking about the engine in a car, we are fueling it with a chemical, petroleum. Okay? That has the potential energy inside it. And then when the reaction occurs, well, we turn that into kinetic energy, the thermal energy, the heat, which moves the piston in the cylinder, and that in turn drives the entire engine of the car. So going from the potential energy and transforming it into kinetic energy allows us to get that car to move. That is a good example of thermochemistry. A more straightforward example of using potential energy is a waterfall. We've got a little tiny waterfall on the left and kind of a roaring giant one. It might be hard to tell by the pictures, but those are people in the one on the right. Okay, it's on a much different scale. So these waterfalls both are generating power. The power is the rate of the energy flow. How much energy is flowing per second. And obviously you can see that waterfall on the right is more powerful. We'd use that word to describe it, more powerful. And if you were to utilize the energy of that falling water for, let's say, a hydroelectric power plant, it would obviously generate way more power, like let's say turn it into electrical power, than the one on the left. So more power comes from both the fact that it is a higher waterfall, it's higher up, so there's a bigger difference in height, and there's just more water flowing for both of those reasons. Either one of them would give you more power. Combined, they give you like way more power. There are certain things in science that are considered to be so reliable that they are considered to be laws. That means they have been thoroughly tested under many different circumstances, much more than just your regular theory, which also has to pass several tests. It takes it to the point where we never see it violated. And that is what we call a law of science. In chemistry, we deal with some of these laws, the laws of conservation. So this is the law of the conservation of energy, the conservation of energy law. The law is very simple. It states that energy is not created and it is not destroyed. Energy can only be transferred and transformed into different forms. So whatever energy you start with, well, it might be in the form of potential energy. It's still going to be there at the end. It might just now be in the form of kinetic energy, or some of it might still be potential, and the rest of it would be in kinetic energy, or some of it might have been turned into electromagnetic radiation. But if you were to add those all back up, you would have the same amount you started with. You wouldn't get any extra, but you also would not have lost any of the energy. So when we add up all the energy in a system, we want to keep track of that and then to see where it winds up, where it goes. So we can see an example of the law of conservation of energy when we look at a little beach bonfire here, a little campfire on the beach. And energy is not being created or destroyed here. It's just being transferred or transformed. What is the energy coming from here? Well, primarily it's coming from the fuel source, which is the cellulose in the wood. And of course, you've got the oxygen in the air around it. Then once the reaction gets going, that energy gets transformed into several different forms. You've got the light that you can see from the fire. That's electromagnetic radiation. You've got the heat from the fire, which is thermal energy. The heat from the fire, the motion of the air molecules. And then you've got the mechanical, the sound of the fire, which is the sort of pressure waves traveling out from the fire, the way that you hear the crackling of that wood. So the energy that was in the chemical bonds in the cellulose and in the oxygen molecules is still there somewhere, but it is found in a different form now after the fire has occurred. When you measure the temperature, what are you really measuring? You're actually measuring the kinetic energy of a system. So the temperature is the measure of the average kinetic energy of the particles in a material. So particles are always moving, like atoms and molecules. They're always moving. At least they're vibrating in place, or they're bouncing around depending on how much energy they have. So temperature scales measure that. And as you know, there's the Celsius scale. Well, that's the one we really like to use on an everyday basis in our labs. That was a very logical one. We talked about that when we talked about the metric system. There is an even better scale, though. There is the Kelvin scale. The Kelvin scale is great because it measures all the way from the lowest possible temperature up. So it's the absolute total temperature. And then, of course, there's the Fahrenheit scale, hard to spell, the one we use in the USA. And it's not really based on anything logical. It's just some random scale that we just got stuck with and are too stubborn to change. But the thing about the Fahrenheit scale is we're used to it, so we know what the temperatures mean. Like you know what I mean when I say 80 degrees Fahrenheit. You might not know what I mean when I say 30 degrees Celsius. You might not know, you might not have a sense of what that means. So I may sometimes refer to the Fahrenheit scale just so you have a reference. But it's really something that is not used in science. Now, we'll be measuring things in our next lab on the Celsius scale. We do not need to convert them to Kelvin in this case, but there are times when you have to. Anyway, all of these scales are always measuring the same thing. They're measuring the kinetic energy of the particles in a material. So when it comes to thermodynamics, the study of how energy flows in a system, there are two fundamental different ways that energy can flow, in reactions or changes. And those are endothermic and exothermic. So endothermic and exothermic, you really have to know what these words mean. And now in both of these it says reaction, and it makes you think of chemical reactions. We do use these in chemical reactions, but I just want you to realize you can use the same exact terms even if it's not a chemical reaction, even if it's just a physical change. You can still use these terms, endothermic and exothermic. So an endothermic reaction is when heat is absorbed by the system, and an exothermic reaction is when heat is released from the system. So it might be hard to think about which one is which unless my easy way of telling which it is, let's say this reaction is taking place in a container, like in a cup or in a beaker. Well, if your hands were outside of that container, and that container was the system, let's say you feel things getting colder. Okay, that means that the system is absorbing heat from its surroundings. You would feel things getting colder if it was absorbing the heat. So that would be an endothermic reaction. If your hands were just outside the beaker, but you feel things getting hotter, that means that heat is being released from the system. That would be exothermic. So the easiest way I find to think about this is if you feel things getting colder around the system, it's endothermic. If you feel things getting hotter, it's exothermic. So we measure this on our thermometers. That's probably the simplest way to differentiate these. That is the end of the notes on energy. We will be utilizing these concepts in our next several assignments, especially our next lab.